Today we're going to review you for a little quiz we have coming up. Actually, it's a pretty big quiz. You have to know how to identify elements versus compounds, predict products based off the state of those products and the reactants that are present in an equation. You have to be able to use the periodic table to determine relative mass, size, and reactivity. And you have to know the regions of the periodic table. And those regions are the alkaline metals, halogens, noble gases. You also have to know where the metals are, the nonmetals, and the metalloids. So our first one, element versus compounds. So we learned that elements are made of only one type of atom. You could look at any chemical formula and know that you have only one type of atom if it's just one square off the periodic table of the elements. So Mg is one square. And even if I didn't have the periodic table in front of me, I would know how many elements I had based off how many capital letters there are. Because for every one capital letter, I have one element. So even though there's two letters here, it's just one element because there's one capital. So one element, one element, one element, one element, one element. So if these two letters were stuck together, like these two letters are, that would be two elements together. And whenever you have two or more types of atoms, or two elements together, then you'd have a compound. So here, these formulas are all compounds. Here's two capitals squeezed together, that's a compound. Two capitals, that's a compound. 1, 2, 3 capitals, so that's a compound made of 3 different elements. Okay, and when we look at pictures, this picture has all the same type of atom. So does this. They can be in pairs, they could be in one big clump, they could be individual spheres, but as long as it's one type of atom, that's an element. If you have two or more types of atoms present, then you don't have an element. So I know that these reds and these whites can't possibly be one element. Instead, I have a compound because I've got this repeat of 2 white H's for every 1 red O. 2 H's, 1 O. 2 H's, 1 O. So a compound is going to be when you have one molecule that repeats over and over again. So I don't have different molecules present. I have this one molecule, 2 or more atoms bonded together, this one molecule repeating 3 times. Same thing over here. I've got this one molecule, a C that has 4 H's attached to it. That one molecule repeats 3 times. So let's see if you can identify elements versus compounds. For the items below, go ahead and identify it as A, one element, B, one compound, or C, neither. Go ahead and pause, try this out, and pause. Okay, hopefully you paused. So I know that this is, the first one is going to be an element because it's just one capital letter, so A for element. Here I've got 2 capital letters, 3 capital letters. That is a compound, B for compound. Here I've got an element, water is a compound. I don't have a single element or a single compound. I've got an element that's in a compound, so that is C. Whoops, that is a letter C. Over here, I have the same type of dot over and over again, so that is an element. Here I have 2 different types of dots repeating over and over again in the same pattern, so it's really just this one molecule repeating over and over and over again. So the plural of the singular molecule, that is a compound, B. Here I've got one molecule. Here he is again. Here he is again. But here's a different little molecule, 2 O's. Here's that first molecule, that second molecule, first molecule. Okay, so I've got different groupings together. It's not just one type of molecule repeating over and over again. So it's not a compound. There's different atoms present, so it's not just one element. So that's C, that's neither. And down here, hopefully you can see enough of it. I've got these 2 little O's, these 2 little O's, and these 2 little O's. They're all one type of atom, so that's an element. And here I've got this one molecule repeating 4 times, so that's a compound. So this was actually that element from number 7 stuck into the compound from number 7. Next on our list, we have to be able to choose the product of a reaction based on its state and based on the elements that are present in that reaction. So real quick, the states are solid, gas, liquid, or aqueous, meaning dissolved in water. So we can look at these guys and see our written equation. If it says it's aqueous, you better have an aqueous thing there, right? So here we go. We can actually rule out the wrong answers for this one. So when aqueous nitric acid is added to copper powder, a blue liquid, and gaseous nitrogen dioxide appear. Okay, so all these are the same, so I'm not going to rule this out. Here's my aqueous nitric acid. Here's my copper powder. It's a solid. And then I know I have to make something that's liquid, so I could look for little L, or I could look for aqueous. And I need a little G. So you don't have either. You're out. Here's little g, little aq. Here's little g, little aq. So it's one of these two. I got to figure out which one is the right gas. So do I have a gaseous copper thing? Let's see. Gaseous nitrogen dioxide. No, I don't have a gaseous copper thing. So I don't think it's this. Gaseous nitrogen dioxide. That makes sense. Do I have an aqueous copper thing? It's a blue liquid. We did learn that aqueous copper solutions are usually blue. So it's got to be this guy. Last equation. All right, so then next, we can use the elements that are present and know the fact that elements can't be created or destroyed to figure out which reaction is a better reaction. So that means that whatever reactant or whatever atoms are present in your reactants, they have to be the same atoms that show up in your products. Otherwise, you would be destroying some atoms or making different atoms. And we don't create them or destroy them, we just rearrange them in a chemical equation. We're not going to talk about nuclear just yet. So here we go. I've got copper solid, which was on your penny in class, added to zinc. We added zinc powder, and we said, oh, we made gold. But we didn't, because that'd be a nuclear reaction. We didn't do that. Where'd the copper go, right? There's no copper in this product. Where's the zinc? Where did the gold come from? No. Did we just take copper solid, add zinc powder, and then we had a blend of copper and zinc? That makes more sense. That's really all we did. Sorry, kids. Okay, so, oops, I skipped one. Skipped this one. Right? No, we did that. Sorry about that. I guess your turn again would have been a better name for this. Oh, I know what I skipped. Sorry about that. No. Never mind. Sorry. So here we go. Let's have you guys try this one. Go ahead and pause and predict the product. Okay. Hopefully you paused. And let's see. I've got burning magnesium ribbon. That would be my solid magnesium. In the presence of oxygen, oxygen gas makes sense for that, produces white powder. So hopefully you asked what state powder is and figured out it's a solid. So that means we're going to rule that one out. Okay, and then we know that we started with magnesium and oxygen, so we need a product that contains both magnesium and oxygen because nothing else was made. So oxygen disappeared for that. That one was aqueous. Chlorine came from out of nowhere here, and our oxygen isn't showing, so it can't be that. So it's got to be this guy. Okay. So let's go ahead and move on to our next one. We have using the periodic table to determine relative size, which means which one is bigger, mass, which one's heavier, and reactivity, which one reacts more. So we learned that mass increases as you go across the periodic table. So beryllium is heavier than lithium and boron is heavier than beryllium. We also learned that mass decreases as you go down. So sodium is heavier than lithium, potassium heavier than sodium. So that's the trend that we see for mass. For size, we learned that size decreased as you go across, which is strange, but we'll understand why soon. So beryllium is smaller than lithium, boron is smaller than beryllium, and size increases as you go down. So we've got sodium getting bigger than lithium, potassium bigger than sodium. They just get bigger and bigger and bigger. And the third one, reactivity, we learned that this corner is really, really reactive, and this corner is really, really reactive, except the noble gases don't react at all. So reactivity increases as you go this way, and it increases as you go this way, up towards the fluorine. Okay, so if we're going to compare lithium versus sodium, okay, well, they're right here. So I know if I'm going to talk about mass, sodium is heavier than lithium. Size, well, size increases as we go down, so sodium is larger than lithium. And reactivity, well, sodium is closer to francium, so sodium is more reactive than lithium. If I compare fluorine versus oxygen, these two, well, I know, let's see, for mass, fluorine's going to weigh more than oxygen. For size decreases across, so oxygen is bigger than fluorine. And for reactivity, I know fluorine is like the most reactive one over on this side, so fluorine's more reactive than oxygen. For helium versus fluorine, it's a little tricky because I know that size increases as we go down, decreases as we go across, but as we take a step down, that's a big jump. So helium is going to be smaller than fluorine. It only has one shell. Fluorine has two. If you can hear that sound in the background, that's my dog crying. I apologize to her. Then let's see. For mass, well, we know that mass is going to increase as we go down. So that fluorine is going to weigh more than the helium. You could also look at the masses on your periodic table. And for reactivity, well, these guys don't react at all. So fluorine is going to be more reactive. So go ahead and try with these four. Compare their mass, their size, and their reactivity. Please pause. Okay, hopefully you paused. So let's see, cesium versus barium. They're right here. So size decreases across, cesium is bigger. Mass increases across, barium is heavier. And reactivity increases as you get closer to francium. So that means that cesium's closer to francium, cesium's more reactive. For iodine versus bromine, right here, well, we know that size increases as you go down, iodine's bigger. Mass increases as you go down, iodine's heavier. And reactivity is going to increase as you go up, so bromine is more reactive. And the last thing we have to look at, or get to look at, is going to be knowing the different families and why families have similar properties. So a family is a column in the periodic table. So lithium, sodium, potassium, rubidium, cesium, francium, that's one family. They're really, really similar in the way they behave. Like they're all soft metals that react with water, and they all bond with one halogen. The reason they all behave very similarly is that they have the same number of valence electrons. And valence electrons are the electrons that stick out, into space the most. So they're the ones that are most likely to react. So since they all have one valence electron, they behave similarly. Okay, so the families we need to know that the first one, these are the alkali metals. The second column, this family, is the alkaline earth metals. Skip over to here. We've got the halogens and the noble gases. Those are the four families we need to know. We also need to know where the metals are, the nonmetals, and the metalloids. So there's this line. You can add this to your paper periodic table. That stair-step line separates the metals are on this side, from the nonmetals. And the nonmetals, except hydrogen is on the wrong side. So hydrogen is a nonmetal. So that's why this periodic table stuck it right here, where your periodic table has it over here. Okay, so the stair-step line separates the metals from the nonmetals. Metalloid, that would almost be like, a metalloid is a little like a metal and it's a little like a nonmetal. It's not exactly like either. So what really happens, it's kind of like if I had everybody line up from short to tall. At some point, I probably wouldn't call you short or tall. I'd probably call you medium. And that's going to be all the elements that are right along the stair-step line. So we'll just say if it touches the stair-step line anywhere, you can call it a metalloid, or you could call it a metal if it's on the left. And if it touches the line and it's on the right, you could call it a metalloid or a nonmetal. You have to recognize it could be either. So questions you could have here is, name an alkali metal. Any of these. Name a noble gas. Any of these. Name a metalloid. Silicon. Something like that. Okay? Hope that helped. See you in class.